So you've got early people looking at things saying there's one thing, there's two things, there's many things. But the way that we talk about things in math is a little bit more formal and also way more complicated. So we're gonna take a little bit of a look at that, and then we can provide it as an exercise for the reader. So if you have ever heard of Zia Vermello Frankel, I'm just gonna throw that on there because without that C you can't do anything fun. These are the basic axioms that outline all of the math that we do. You could come up with a different set of axioms that would give you a completely different system of math, but we're gonna stick with these. And in particular, for building numbers, there are a couple basic ideas that we have. The first one being that in the beginning there was nothing. And we call that nothing the empty set. Or for our talk today, we're gonna ignore this and say that this is actually zero. There was zero. And there is another axiom that, I mean, you have to combine a bunch of them, but the basic idea is that if we have zero, which we do, congratulations, then we have a set that contains zero. Way to go. And if it contains any element n, it contains some next element that we're going to denote s of n. We're treating this as a function. Is that too low for some people to see? So we are treating this as sort of a next element. In other words, this is often known as the axiom of infinity. We have infinitely many things, and in particular, we have the set of natural numbers. We have zero, so we have some next element. Let's go out on a limb here and call it 1. We have 1, so we have some next element. And so on and so forth. I would list them all out here, but I think I'd run out of time. So we've got this whole set of these elements, one after another, and we will denote this set the set of natural numbers with 0. Oftentimes when we're using the set of natural numbers, it's convenient to ignore 0, to leave it off of our set, but sort of the natural construction of it using these axioms gives us this whole set. But these numbers aren't actually all that exciting yet. These are still early math concepts of numbers and 0 as well. So all we can really do with these things is count. We can say, okay, we have a first element, we have a next element, we have an element after that. In other words, for any n, we can move to the next element, s, and then the next set, and then the next set. So if you wanted to count things, you might start off with some n in our set. And you might say, okay, I've got my next thing. Okay, I wanna keep going. So I've got another element after that. And I've got another element after that. And I've got another element after that. And so on and so forth. And what you might find is that what we're doing is some sort of iterated counting process. We're starting off at some number. And we're continuing, let's say, I have used my numbers to count that there are m times that I am iterating this counting operation. I am moving to the next element m times. So if I wanted to write this a little bit cleaner, I might write something like this. To this operation, and I am applying this counting operation m times. And this is a little bit clunky notation, so let's go out on another limb here and maybe come up with a bit of a cleaner notation. Some way to combine these two numbers, maybe n, m, and let's do something like that. And let's go ahead and call this something. Let's call that addition. So just from this sort of definition, and I am, believe me, if you were doing this directly from this, we would not be anywhere close to this step yet if we were going all the way back to the base axioms. But just sort of a loose following of this chain, we have constructed this addition operation. It follows naturally from sort of this normal counting operation. Okay, so I've got the natural layers, and I can add things. I can count things. But it might help, since we've got addition, to be able to say, okay, but what if I want to go the other way? What if I wanted to do something completely crazy, like I can apply s, count m times from 0, and this would give me m. But what if I wanted to count m times from some n, or just to simplify things, I want to count 1 time from some n and get 0. Well, if I look at my list of natural numbers, clearly what I have is incomplete. I don't have any element that comes before 0 that I would be able to count forward to get there. So, naturally, we might decide, let's expand this out. Let's take this element here and say, okay, n is defined in this. It's the number that if you were to count forward 1, you get 0. And you could do the same thing. If I were to count forward twice from something, I want 0. That would be our sort of negative numbers. So doing this process, we get the integers by adding additive inverses. That's all we've done. We've said for every element, we should be able to add something to it to get 0. In other words, we're sort of allowing for subtraction there. Okay, so we've got the integers. We can add things. Everything is fine and dandy. But what if I wanted to add things a lot of times? I think most of you are probably familiar where this discussion is going. If I wanted to add some number n to itself a bunch of times, let's say m times, again, this is a bit clunky. So we might naturally decide, let's define some notation for this, call this an operation, multiplication, and now we have multiplication. We have another operation. If you wanted to get really far down into the dirt and dig through these details, you find that addition and multiplication, of course, are exactly the addition and multiplication operations we're used to. They are both commutative, which means that you can reorder elements. M plus n is the same as n plus m. We should have used more distinct sounding letters to demonstrate that point. And we've also got associativity, that classic a plus b, and then adding c is the same as a plus b plus c in that. And the same idea with multiplication. Okay, so let's just go ahead and jump to that next step, because I think we all know where this next step is headed. We had addition. We wanted to be able to subtract. We wanted to have these additive inverses. So we threw in the negative numbers and got the integers. Now we've got multiplication. So now let's answer the question, what happens if I want to be able to divide by number, to do the inverse of multiplication, find these multiplicative inverses? Well, do that. And now suddenly we've got Q, the set of rational numbers, all these fractions of integers. And we've done this by, I don't know why whenever I write multiplicative inverses, I write first. It's bizarre, but it's happened twice already. So we've added in our multiplicative inverses. Well, going forward from here is actually way more complicated than anything that we've done so far. I think naturally, we all know what the next step is. We all know where we need to end up. We need to end up with the real numbers. But how do we get to the real numbers? There's nothing with additive inverse, it's something with multiplicative inverse. There's nothing we can do with the operations that we already have that is going to get anything more than Q. Q is a field that has additive and multiplicative inverses. It's a very nice context. Unless we start to take a look at these gaps that naturally occur in the rational numbers. There are, in some sense, things missing, these holes that we might be able to fill. So let's forget all about multiplication. And let's talk about how to fill in these gaps. So we're just going to go ahead and talk about on Q, we define this completely crazy and wild map, the absolute value. We define this by the absolute value of M, or let's say Q, since we're in the rational numbers, is going to be Q if Q is greater than or equal to 0, negative Q if Q is less than 0. Since we're still in the rational numbers, we can still order everything nicely. So we can define this, again, sort of nicely speaking. I'm sure if you really wanted to get down into the details, you could do that and have no fun with yourself. But so we can define this absolute value. But now we start to run into an issue. Because if we use this absolute value to determine how far things away are from each other, then what we might end up with is numbers that get very, 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 very close to each other and yet don't reach some sort of limiting point. Brace yourselves. Cauchy, this is some guy, he's a mathematician, and he came up with this nice idea of Cauchy sequences. For all epsilon greater than 0. Now, try not to get too mad, because if I'm allowing this to be a real number and real numbers don't exist yet, we're just going to ignore that part. I guess if you wanted to use this as a natural number and say less than 1 over n, we could do that, but we're just going to write this for now. So for all epsilon greater than 0, there exists some n in the natural numbers. Of course, these natural numbers do exist. We created them. And this is going to be about some sequence of rational numbers, some list of elements where this index just keeps going. For every element, we've got a next element. It's, in some sense, bijective to the natural numbers themselves. So for every epsilon greater than 0, there exists n in the natural numbers such that the distance between these points less than epsilon for all m n greater than or equal to big N. This is a really, really complicated way of saying the numbers get really close to each other. As we continue on in our sequence, for every point, for every distance that we'd like to be between our points, we can find a point in our sequence where now everything over here is within that distance of each other. So this is constitutes. We also have an idea of convergence, also of one of these sequences. Convergence says that there exists some x, and I'm not going to say where it is for now, such that for all epsilon being 0, there exists big N in the natural numbers, yada yada yada, less than epsilon for all n greater than n. Again, a lot of math speak for saying convergence, we have some limiting point that all of our elements get very, 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 very close to. No matter how close we want our elements to be to this limiting value, we're going to be able to reach a sequence, a point in our sequence where everything after that is within that defined distance from our convergence. Okay, well, in some sense, it seems like Cauchiness, where they're getting close to each other, and convergence, where they're getting close to a specific thing, should be the same, right? But not so. Because so far, all we have is the rational numbers. And consider the following sequence of rational numbers. Let's actually go with 1. Okay. You agree that that's a rational number? Yeah. 1.4. 1.41. 1.414. That's all the numbers that I know.
2136.
Sure. So this, I think you would all agree, is a sequence of rational numbers. They terminate in their decimal expansions. We're not even going to get into how that works with all of the stuff that we talked about, but they terminate, so they are rational numbers. And I think you might all agree that if the real numbers have already been built, that, and I can find more numbers, that this is going to converge to the square root of 2. Okay. Square root of 2 is, that could be a number, it could be a rational number. But as it turns out, we've got these gaps. Even though these numbers are getting closer and closer and closer and closer to each other, there's that gap that they're approaching, but there's nothing there to fill it. And how do we know that the square root of 2 is not rational? Through a nice fancy proof that says, okay, suppose that it is. Suppose that it's a rational number. You don't know. You don't know that it's not rational. So let's assume that it's rational. Square root of 2 is some integer m over some hopefully non-zero integer n. Okay, so this means that the square root of 2 times n is equal to n. And now let's square both sides. We don't know what square root of 2 is yet because of all of this mess. But the one thing that I do know about it is that if I multiply it by itself, I should get 2 now. So this is 2 n squared on the left side, m squared on the right.
So do you need m and n GCD1?
Sir. Yes, we could do infinite descent, but yes, since we have written these as integers, thank you, we can assume that we reduce this.
Or you can just count the factors of 2 on this side.
We could also
not.
Either way. This actually is probably, there we go, I just wrote it, I didn't actually say what it was. It's a lot easier to see it if we assume that we've reduced this fraction. Again, we haven't shown that, but if you really want to get into the weeds, you can do that. Show that you can reduce all of your numbers. So we've got 2n squared equals m squared. Can anyone tell me the one thing, or one of the many things, but the most important thing that we know about the number on the left side of that equation?
Even.
It's an even number. Right, it's 2 times some integer, so it must be an even number, which means that this is even as well. Which means that, in fact, m has to be even, because you can't square an odd number and get an even. That's Just ridiculous. So we can write this, let's say m is 2n prime. Weird notation. Write this as 2m prime, and suddenly over here, we've got 4n prime squared. Cancel out a factor. Well, now this is even, which means that n squared must be even. But then 2 divides n as well. And so 2 divides both of these, contradicting the fact that they were supposed to have GCD 1. Okay. So we've got this gap. We can agree we've got this set of rational numbers, a sequence of rational numbers that converges to, in what some sense should be a number, but we don't have it in the rationals, the only numbers that we have. Okay, well, that's not too big of an issue, right? You just say, okay, that number exists now. We can, if we want to, we can just keep going, keep sending those decimals out to the right. For every Cauchy sequence, every set of elements, every sequence of numbers that get closer and closer to each other, just define some limit. I mean, there's a lot more work to it than that. We're not going to get into today, but you're going to find that that's a theme throughout this whole thing. But we can just define that there is some element that should get close to. To put this in fancy mathematical terms, we are completing Q with respect to the absolute value. All of that means is there were these gaps. Now we have filled in all of these gaps. Okay, well, surely now we're done. We've taken these additive inverses, we've taken multiplicative inverses, we filled in every gap. Certainly you can have no more complaints that this is not all of the numbers that exist. But I think you all know that that's not correct. Because some smart aleck came along and said, I don't like this. And said, I can take the square root of 2 now. These new numbers, I've constructed them. I can take their square root. So why can't I take the square root of -1? You can't tell me that I'm not allowed to take the So gosh darn it, I'm gonna do it. And I'm gonna call this I. And unfortunately, these became known as the imaginary numbers. They make a whole lot of sense to exist if you really get down into the weeds of it, but for better or for worse, they are called these imaginary numbers. And if we take these real numbers and we say, okay, we want I to exist in here, and for any two numbers that we have, we should be able to add them together, and we should be able to multiply them together. To make sure that we're not missing anything, we should throw everything we have at this I so that you will finally be satisfied. And so these numbers are going to look something like A0, this A1 I, plus A2 I squared, plus A3 I cubed. And we're gonna terminate this at some point, where n is a natural number, and these AIs are real. These are real things that exist. Except it's actually a lot simpler than that. Because what is this? It's -A2, which means that this we can just absorb into that. And this we can absorb into that part. So this is -A3I. And so on and so forth. Again, if you really wanted to be exact about it, you could show a little bit more work. But it is actually going to be enough to consider just elements A plus BI, where A and B. And I don't want to have to write this every single time that I'm going to refer to this. So let's do something really crazy here. And call this a set of complex numbers. I'm allowing things to be real, I'm allowing things to be imaginary, despite the name. And I'm allowing everything that is a linear combination of a real part and an imaginary. So now I've got the complex numbers, added in. Now, surely we're done. Surely this is all of the numbers that could possibly exist. But let's actually take a closer look at this part, this going from R to C. Because if we think about it a different way, instead of saying, I want some element to exist, that is the square root of -1. What if I instead said, I want a root of the polynomial x squared plus 1. I think you'll all agree that this does not have a root in the real numbers, because if anything squared plus 1 is equal to 0, then x squared is equal to -1, and again, we've got the plus or minus square root of -1. And okay, we can do that. We can rephrase this a little bit. There's nothing wrong with that. Except what's so special about x squared plus 1? Why does this polynomial get special treatment? What if I instead make a f of x that's the polynomial in Rx, the polynomial ring. What if I instead say, okay, give me any irreducible ring? Degree of f greater than or equal to 2, because otherwise we're just throwing on more real numbers. What if I pick any polynomial over the real numbers? And instead of throwing in this golden child I want to pick this other root. Well, as it turns out, any such root let's say alpha, is already in the complex numbers. The complex numbers are algebraically closed. This is the algebraic closure of R. We don't need to throw in anything more because it already existed. And if we write this as A plus BI, where B, of course, is not 0, because otherwise, again, it's just another real number. Can't throw a real number out of the real numbers and suddenly get complex numbers. If we have this element, well, then surely if alpha is in some set, well, we've got the real numbers here. We already built the real numbers. We know they exist. So alpha minus A. And we've got multiplicative inverses, which means that we've got the inverse of B. We can divide the B across, and wouldn't you know it, that golden child lying. So, no matter what bizarre polynomial you decide to throw on here, as long as it is degree greater than 2, you don't technically need that it's irreducible, but you need that it has an irreducible factor with degree greater than or equal to 2. So we're just gonna assume that it's irreducible with degree greater than or equal to 2. No matter what polynomial I pick, toss on a root, suddenly we've got the complex numbers. Okay, so there we go. That's all the numbers. You can all leave. No, don't actually. Because what I wish that I had that kind of comedic time. Because it seemed like we started off with this very natural set of numbers from these axioms. And we did the next natural thing, additive inverses, multiplicative inverses. This one's weird, but we did it anyway. And then we threw in I, or any root of a polynomial that's irreducible to be greater than or equal to 2. And we constructed all the number systems. But you may not see it in here. We actually made a number of choices. To get to this point. So let's take a look at some of those choices that we made and see what if we made different choices. So what if these were not the things that made the most sense to do like they do in our universe? First of all, the biggest choice that we made is this one right here. It's the sort of least natural step, you might think, but this did involve a choice. Because even though the absolute value that we used makes a lot of sense in our universe, so saying that how big something is how far away it is from 0. It's not the only absolute value. So let's talk about what an absolute value is. We've got 3, or let's split one of them into 2 conditions. We've got 4 conditions. Things that, based on what our absolute value does, we would hope that every absolute value. So can anyone tell me one of the very, very nice properties of the absolute value that we would want to carry over? Yes, Trevor.
Triangle inequality.
Triangle inequality. Not the first one. But yes, triangle.
It's the most important.
It's the most annoying one. The triangle inequality. If we've got a triangle, the length of 2 sides added up should be longer than the length of the 3rd side. In other words, the shortest distance between 2 points is a straight line. And we write this as for all x and y in Q still. The absolute value of x plus y is less than or equal to absolute value of x plus absolute value. You could also write this with a negative, wouldn't make a difference because the absolute value of negative y is the absolute value of y. Okay, we've got the tough one out of the way, so can anyone give me another one, someone that's not Trevor?
The distance between a point and itself is 0.
The distance between a point and itself is 0.
You mean-
Yes, we're not talking about a metric.
Oh, sorry. Okay.
Yeah, we're just looking for the absolute value. Yeah.
I like my absolute values to give me an absolute distance, always positive numbers.
We should always get positive numbers, right? So for all x in our rational numbers, I would hope that the absolute value of x is greater than or equal to 0. We shouldn't get negative distances between those things because that makes no sense. This second one is very closely related to the first. So we said that it has to be greater than or equal to 0.
Only assign 0 to 0.
Yes, the only thing of size 0 should be 0 itself. Anything else has some sort of magnitude that we can make. So absolute value of x is equal to 0 if and only at x. Now what's the last?
Absolute value of product.
Yeah. The absolute value of a product of 2 things. We've already talked about the absolute value of sum of 2 things. So let's address the product of 2 things. Well, it should be ideally multiplicative. You can go ahead and check that our regular absolute value has all of these very, very nice properties. And yet, it is not the only function that has those properties. Again, keeping with our running theme, we're going to skip a lot of steps coming up. But it turned out that for any prime p in Z, Nobody asked me what a prime number is. We didn't. But for any prime number in Z, we can define an absolute value that has to do with P. You might call it some sort of p-adic absolute value. That was a completely unnatural. We can define this absolute value by, for any x in our rational numbers, well, we should be able to write this as a fraction of integers. Again, let's assume that n is not 0 because we don't want to deal with that. For any x in our rational numbers, we can write it as a fraction. And because these are integers now, we can pull out all of the factors of p and just treat those separate. So this is going to be m over n times p to the a, where GCD of m and n is 1. We've reduced it. That part doesn't really matter for our purposes. And p does not divide m. And p does not divide it. We pulled out every single factor of p that we can. Okay.
How do you like your triangle?
Let's go ahead. Let's go ahead and say that this is a non-zero. Because it's pretty hard to do this uniquely if we let 0 be in the party. So we've done this. Let's go ahead and define that absolute value, shall we? That the absolute value of 0 is 0. Yay. And for the absolute value of for x not 0, absolute value of x, we can write this as the absolute value of m over n times p to the a, be p to the negative. So the more times p divides something, the smaller it is. So in this system, let's say p is 2, 10 trillion, well, it's divisible by a lot of 2's. 10 trillion is a very, very small number. Whereas 1 over 10 trillion, well, that's got a lot of 2's down in the denominator. 1 over 10 trillion is a very big number in this number system. Okay, well, we have this other absolute value. How does that help us? Well, what we did before was we completed Q. Let's go ahead and do that. Let's instead make another branch, and we're going to complete Q with respect to the adic. Absolutely. Now, technically, this should be infinitely many arrows. We've got 2 adic, 3 adic, 5 adic, 7 adic.
Right, in the sense that you're going to use Cauchy sequences again, right?
In the sense that, yes, we are going to use these Cauchy sequences, numbers that get very, very close to each other under this weird absolute value, but which don't exist already. So, something like, let's write these in base. Somebody pick a prime. I like 3. So let's write these base 3. Let's say that my numbers are 1, 0. Let's say 1, 1, 0. So this is 3 plus 9. This is actually 12. Let's say 2, 1, 1, 0. 1, 2, 1, 1, 0. 2, 1, 2, 1, 1, 0. 0, 2, etc., etc. So we've built all these numbers. And now, notice something here. If I pick any of these numbers over here, and I subtract them from each other, what do I get? Well, here, the difference of these is 10,000, base 3. The difference of these is 21, 210,000, 210,000 base 3. And the difference between these is 200,000. Now you'll notice all these trailing zeros, and those trailing zeros mean that it's divisible by 3 a bunch of times. These are all divisible by 3 to the 4th, which means that actually the p-adic absolute value is 3 to the negative. So these are numbers that, even though in our regular absolute value, they're getting really big and really far apart under this p-adic absolute, they're getting very, very close to each other. And if I were to continue this process, well, I can have any number of digits to the left of the decimal point that I want, right? Where in the rational numbers, I get as many decimals to the left as I want. Except that I can't have infinite. That would be ridiculous. The sequence, or the series rather, p to the k, I think you'd all agree that this diverges, right? This number of infinitely many p's, this should end up going to infinity. Except that this actually converges in the p-adic absolute. These are elements that we can consider. Elements with infinitely many digits to the left now, because we've defined this Cauchy sequence and this Cauchy sequence having some thing. So we're going to write this. Sometimes you'll see it written as that, the p-adic numbers. And these numbers are really bizarre to think about. You get used to it after a while. But what these numbers look like is A0, so that's a p to the n, A0 plus A0p plus A0 squared, so on and so forth, where n is any integer, and ai is some number, some digit mod p between 0 and p. So we've actually got these infinite sums. Well, because we've completed with respect to the p-adic absolute value instead of the standard absolute value, this is a number. It may not be as real as we like, but it does exist. This is a different choice that we could make. And if we were living in a different universe where this p-adic absolute value made any sense, that is something that might come very naturally to us. In other words, we might write this as A0, A1, 2, 3, 4. We might write it in this base p, where we actually only have finitely many digits to the right of the decimal places, placing infinitely many. So that is the p-adic. Again, a context that might arise if we made simply different choices. But what if we made even more different choices? You can see, you might even see a crazy look in my eyes. Get excited about talking about this next step. Because, well, okay, we took additive inverses, multiplicative inverses, we completed with respect to some metric. And then we added in these roots of these polynomials. Certainly we could do that again here. We could add on more roots of polynomials. There are things that exist beyond this as roots of polynomials in this, but we're not going to get too much into that because I don't want to talk about that. What I do want to talk about is there any reason in particular that we had to do everything in this exact order? Is there any particular reason why adding in roots of polynomials was the last thing that we had to do? I don't see any reason. What if, instead of going through this branch, we instead decided right here, let's add on a root of a polynomial. a root alpha of some irreducible f of x. It's not quite as nice to write as some of the other ones, but we can certainly do this. If we add on a root of some irreducible f of x and q of x. Now, I'm not saying that these are new numbers, because certainly if it's a root of something in qx, it's a root of something in rx, and we already said that anything like that is a complex number. So anything that we're getting here is still going to be complex, but it actually creates a different ring that we can consider. Actually, it creates a field that we can consider. It's going to look like irrational numbers adjoined to some alpha. I see you saying parentheses. It's actually the same. In this specific context, where we are allowed to divide these rational functions evaluated at alpha versus polynomials evaluated at alpha. In this one specific case, it actually ends up being the same. But we're not going to get into that. Again, keeping it the theme of this topic. So we can add on these extra integers, or add on these extra numbers. And this is something that we would call a ring. A number. I didn't remember where I was. But it turns out that if we add on these roots here instead of over here, we can get any number of different fields. In fact, the number of for every alpha that we can add on here, if it's roots of different polynomials, we're going to get these different fields. Not always. So, adding on different elements here, we haven't gotten all. So, I'm just going to go ahead and bypass this over here. Instead of adding on just one root, I'm going to get really crazy. Add on all roots of any f of x in my polynomials. So if I just go completely nuts, and instead of just adding on one, I add on everything, this is what we would call the algebraic closure. Or you can call it the integral closure, it's the same thing. It's in one very specific case. This is the set of what we call algebraic. Now, looking at my paper here, my nice diagram that I've drawn, there are a lot more things that I have written on here that I don't want to talk about because it would get boring pretty fast. We've seen most of the interesting stuff. There's a lot more interesting stuff that I could talk about, but you might not all find it interesting. So I'm going to end my talk by saying, okay, what is a number? Because if you ask most people, what is the most fundamental type of thing that is in mathematics, most of the people that you ask are probably going to say that a number is the most fundamental thing that exists in math. And yet, all of this mess, I think we might all agree, are numbers in some sense. At least if they're not, calling these p-adic numbers and complex numbers is a mistake. So in some sense, we might think, okay, well, what is a number? Well, we started off with the natural numbers, just anything you can get from extending the natural numbers in some way is a number. But that's a lot of things. And a lot of things that you might not want to call a number. Like 5x² plus 3x plus 2. Well, I did get this from extending the natural numbers in a reasonable way. But if I came in here and called this a number, I think I'd be kicked out of the math department. They're, you know, going too hard. So, what is a number? The answer is, I can't tell you. I even Googled it and it didn't come up with anything useful. Because there are infinitely many ways that we could have perceived. I assume. I haven't actually done all of them. But there are all sorts of different ways that we could have perceived. There are any number of different things that we could call numbers. So putting numbers into a box doesn't really make sense, even though it is, in many senses, the most fundamental type of thing you can do. It has no definition. And I think that's where I'll end my talk.
Any questions?
Yeah,
What do you say to somebody who learns about the definition of the real numbers and says, so the initial extension using our normal alphabet, and says, I just don't think that anything in R minus Q, so any non-rational real number is a number, like, because what recourse do you have when you ask me what E is, other than to say, it's the limit of this sequence?
and that's exactly one of the things why defining what a number is so hard. Because, yeah, there are infinitely many things you can extend this. You could certainly call this a number. Some people might even consider this a number if they were, you know. But drawing that line in the sand is a pretty hard thing to do, and you certainly could draw a line in the sand here. But again, I think some people might call you a bit pedantic. So saying exactly what is and is not a number, it almost doesn't make sense to define. Doesn't make sense to draw lines in the sand.
I've always thought it was kind of ironic, you know, everybody's got a different opinion, but I've always thought that imaginary numbers were ironic because square root of 2, I, any of those things, I can build it. It's an algebraic construction. I didn't build it. E, pi, that's a little more flaky for me, right? Because that one, you can't construct that really algebraically. It's limited at sequence. Other questions?
Okay, so you said maybe we shouldn't get into it, but I'm curious if you could maybe tell us a little bit more about how you would show that multiplication, the way we defined it as the condition, is commutative. Maybe you can suggest how you would do that without changing the reason.
Show how it's commutative.
Yeah, so you said that the addition and multiplication are commutative.
Yeah. So one simple argument that you could do, and again, I'm gonna a little bit oversimplify. We've got m plus n plus m plus n times. Again, I really should pick different letters that sound less similar. But if I've added all of this up, okay. Well, what do we know about m? Well, I know just from basic the counting property of this and how addition is defined. I can write this as a sum of ones, right? So on and so forth. And now that I've constructed all of these things, and bear with me here because I'm going to use associativity to show commutativity. You have to do that other part, which is actually, I think, a little bit easier. Instead of adding them in this order and then adding across, let's add in this order and then down. Now I've got n added m times, and so multiplications. assuming that you assume that it's associated.
Other questions? I have questions. On your big diagram, did you have the surreal numbers on there?
I do not have the serial number.
Okay.
I didn't want to touch the serial.
What are
That's like
the,
some of the, what's that?
what are the surreal numbers?
We're not touching. Yeah, we need to find some mushrooms. Yeah, it's sort of like infinitesimal. We can talk, I mean, I actually used it to prove a theorem in a paper and I don't really understand it myself. I learned just enough to be able to prove the theorem. How many of you have ever heard of Principia Mathematica? Yeah, it was written by Russell and Whitehead, like 1910, or that maybe a little bit. Anyway, the idea was this was before Gödel came along, knocked everybody down. But anyway, they thought they would like, sort of really put mathematics on a strong footing, right? And maybe you could even reduce proof to syllogisms, things like this. I have the Principia volume. So here's your homework. Go to the library, just look at it. When you open the first volume, I mean, it reads like it's like wallpaper designed by the serial killer guy from Seven, right? I mean, I can't even believe they wrote this stuff down. You just can't even read it. And on page 362, they proved that 1 + 1 is 2. And it's like, actually, Russell said that sort of intellectually, it sort of broke him. So these are not simple things when you really get into the weeds, as you say. So
And if you really, really want to get into the weeds, it'll take you a little bit, but it is really fascinating. Look up these axioms and try to do anything.
okay, that's. All right, mark your calendar for next week, and let's thank Grant again. And pizza, take it home. Be the hero of your dorm, whatever. Food should be gone. I was sorry.
I appreciate it.
About all you out there.
You didn't say that.